So now I would like to turn it over to Dr. Stephen Fallis of our NOCWD Research Department, and he is going to be introducing our special guest today. Thank you.
Thank you. It's my pleasure to introduce our first speaker in this series today, Professor Larry MacMillan, University of Princeton University. So he was born in Bellshill in Scotland, and he attended Glasgow University where he got his bachelor's degree in chemistry. By the way, that's a really good university. I really recommend everyone bear that in mind when they think about where they're going to school with their kids. So he got his bachelor's degree at the University of Glasgow, and then he went over to Caltech, to UC Irvine, and he worked on his PhD there with Larry Overman. And upon getting his PhD, he went to Harvard University, where he did a postdoctoral fellowship with Dave Evans. He began his academic career at UC Berkeley, and then he moved on to Caltech, where he was there for about 6 years before he moved over to Princeton University. And he's been at Princeton University since 2006. He was the Barton Hepburn Professor of Chemistry. He also chaired the Department of Chemistry from 2010 to 2015, and currently he's the James S. McDonnell Distinguished Professor, University Professor of Chemistry, and also a Ludwig Distinguished Scholar. In 2021, he was awarded the Nobel Prize, which he shares with Benjamin List, for the development of asymmetric organocatalysis. And a year later, in 2022, he was knighted by Queen Elizabeth II. It's a real pleasure to have you here to kick off our talk, which is titled Capacity to Discovery in Atoms.
Okay, thank you, Steve. I think I'll. Oh, I can't use that one. Use that one. Yeah. That was an intelligence test, and I just failed it. Okay. Thank you for coming out today to see this talk. I'm really excited to get a chance to be here today. I travel basically all over the world giving chemistry talks, and I've never had an opportunity like today to come to a place doing the kind of work that everyone here is doing. So I wanted to thank you first and foremost, and I'll thank you again at the end for the opportunity to do this. This has already been very special to me, and I think it will continue to be. But just the chance to meet all of you and see all the different things you're doing and think about all the different problems you're thinking about has been sort of honestly educational and fascinating. I've also never, I don't know what kind of room this is, but I've never given a talk in a room like this before. And I've certainly never given a talk where someone's put a banner up of my soccer team from Scotland. I don't know who, I think Steve did that. Thank you, Steve, for doing that. It's made me feel very much at home, actually. All right, so what I'm going to do today, I talked to Patrick about what kind of talk should I give. And his feedback was really tough. It was really tough. He said, well, there'll be a bunch of chemists there, but there'll also be a whole range of people who are not chemists, and there'll be some engineers, and there'll be some other people who don't even think about science. I'm thinking, all right, what kind of talk is this going to be? This is going to be a tough talk to give. So what I thought I would do, I would give you an overview of about basically who I am, my career in a very general sense, hopefully digestible to people who are not chemists, for about maybe 30 minutes of it, maybe 35. And then for the last 15 minutes, I was going to get very technical about some of the recent things that we've been working on. But we work on a lot of different things. So the one thing I'll say is if any of this grabs your attention and you feel like talking more to me about some of the things we're doing in our lab, feel free to reach out, email me. I'm happy to jump on Zoom. and go into a lot more detail about any of the things we're working on, because that would be fun for me too. All right, so enough not showing you any slides. Let me actually sort of move into some slides. So I was going to just start off and tell you where I'm from. Now, I travel the world, and I often use this as my opening slide. And so, as you can probably tell, I'm not from Brooklyn or New York. I'm actually from somewhere else. I'm from Scotland. And I think through Steve, you're probably well trained to the Scottish accent at this point. But I always like to show this map of where Scotland is. And you might find that a little bit insulting that I'm showing you this, but trust me, there's so many people in America have no idea where Scotland is. So that's why I always like to start off with this slide. Now, there's a really easy way, and just indulge me for saying this for a second, there's a really easy way to remember where Scotland is. And this is the mnemonic I teach everyone, that Scotland is always on top of England. So if you remember that, you're set to go. All right, that joke works everywhere except one country. All right. All right. So where I grew up in Glasgow, which most Americans have heard of Edinburgh, but Glasgow, in my opinion, is the better city. It's not as picturesque, but the people have it's a very fun city to go visit because of the people who live there. They've got a great sense of humour. I grew up in this little town called Bellshill. It's a steelworking town in Scotland. My father was a steelworker. My mom was a home help, which is kind of like a maid for people in the neighbourhood. And this is basically where I grew up. I hope you can sort of see this. This is our council house where we grew up in. And this is a photograph of our family from the 1970s, which you can tell based on the hairstyles and the wallpaper, etc. And I always tell people, we grew up, we didn't have much money. We certainly didn't have much money, but we were very wealthy because we laughed every day. And that's a common thing in Scotland, is to have good humour and to interact with people with good humour, which is something which has been critical and key, I would think, for my upbringing. It really was a fantastic place to sort of grow up. Okay, so when I was relatively young, my brother, he decided to do a remarkable thing. And the remarkable thing he decided to do was he decided he wanted to go to university. And you'd probably think, well, why is that remarkable? Well, in my town, we didn't have anyone who'd ever gone to university before. No one from my high school had ever gone to university before. And he decided he wanted to do this. And this was quite controversial. My mom and dad thought he was just being lazy and trying to avoid going to steelworks, which was probably true, actually. But he decided he wanted to do this, and off he went to university. And he got a degree, and he got a degree in physics. And right after he got his degree, he got a job. And the job paid more money as a salary than what my father was making as a steelworker after 30 years in steelworks. And it was at that moment that my mom and dad came to see me and said, "You're going to university." So I always like to tell people my biggest educational decision of my life was not made by me. It was made effectively by my brother through my mom and dad. So I went off to university to do physics, because that was the formula. My brother did physics. I was told I had to do physics. But I was absolutely terrible at physics. I was just appalling. But very fortunately along the way, I had to also do chemistry courses. And I realized I really fell in love with organic chemistry. Organic chemistry is something I enjoyed and I could really do. And I also had this fantastic group. This is the graduating class from 1989 of Glasgow University. So at the end of this time, and whenever I give talks now, I always say to, especially younger people, you know, education really is your passport to the world. And one of the ways I like to sort of state that is because once I got my bachelor's degree, I decided what I wanted to do was I wanted to go to America. I wanted to go to America to do a PhD, because to be perfectly honest, I'm not just saying this to kiss up to Americans, but I was totally in love with the idea of America. I loved American sports. I still do love American sports and the NFL. I loved American television, you know, things like Starsky and Hutch and Cheers and things like that. And for some of the younger people, you can ask your mom and dad what Starsky and Hutch is, but I really loved America. So I used this and I thought, well, maybe I could try and get a PhD in America. So what I did was I went out and I got these things called airmail envelopes. These are airmail envelopes. This is before the internet, because I am very old. And airmail envelopes were how you would write to people in different countries. And I saved up and I bought these, and I wrote to individuals in different institutions in America asking if I could do a PhD with them. And basically, I sent 18 letters over 6 months and get absolutely no reply. I was just about to give up, but the 19th letter, I received a reply. And I received a reply from this gentleman. The picture shows up. This is him here. His name is Hal Moore. He was a dean and he was a founding faculty member at University of California down in Irvine, just down the road. And he sent me a nice letter. And it basically, the letter effectively said, "You're an idiot. You can't get a PhD in America by writing letters to individuals. It just doesn't work that way." So he actually sent me this application form. And this is I still have the application form from 1988, actually. And imagine this scene, you know, I'm over in Scotland, in Glasgow, and Steve will tell you, it rains basically every single day in Glasgow. And all of a sudden, this shows up. And here you have this guy in a t-shirt, and he's wearing shorts, and he's skateboarding through a park. This looks fantastic, right? So at this moment, I decide I'm excited about this. So I send off my application, and lo and behold, I was accepted to come over to UC Irvine in January of 1990. Now, it was a culture shock in so many different ways, but it was a fantastic culture shock of coming here to Southern California. And one of my sort of favorite moments that I love to tell everyone, I remember I had to go out and find an apartment. And I remember going to this one apartment complex, and this one lady took me around an apartment complex and said to me, you know, here we have 4 swimming pools, we have 6 tennis courts, and we have 8 jacuzzis. And I always remember looking this woman in the eye and saying, "What is a jacuzzi?" And she said to me, "It's a big hole in the ground, you fill it with hot water, bring a 6-pack of beer on a Friday night, you'll have a great time. You'll have a great time." And it turns out she was absolutely right. So that was me in the jacuzzi, and that's when I decided I love California. California is an amazing place. All right, so that's the beginning about me. Now I'm going to jump in this story to 2021, which is when I found out, literally on this day, that I won the Nobel Prize. So I'm going to jump around a little bit. And actually, because I was given another talk on Friday where they asked me to bring the Nobel Prize with me, I actually have the medal with me. If anyone wants to take a photograph at the end, you can come up and take a photograph. I keep it in a sandwich bag, just for protection purposes, but I'll take it out of the sandwich bag for people to sort of check out. Anyway, but so in 2021, we won the Nobel Prize, and one of the first questions that people always ask me, you won it for this thing called organocatalysis. And the first question is, what does that even mean? Organocatalysis, it's such a weird word. So what I like to tell people is to explain it is, and I know most people here will know what catalysis is, but this is the way when I give, you know, really briefly when I give talks to, for example, non-chemists or high school students and explain what catalysis is. I show them this photograph of my office, but you can pick anywhere, like even in this room. And if you look around, you realize that absolutely everything that you can see that's right in front of you, or you can touch, is made by a chemical reaction. Absolutely every single thing. And so if I look at my office and you look at all these different things, which are these bubbles that are popping up, these are all these different things in my office, and those are all the chemical reactions that make them. Okay, now if I hone in on this one right here, that's my coffee cup right there on my desk, and this chemical reaction right there, that's the chemical reaction to make caffeine. We know caffeine's the key stimulant in coffee. As it happens, most chemical reactions require energy. Most of them are not spontaneous. And the way that we chemists represent this, and at this stage I'm not going to get technical yet, but the way we represent this is something we call an energy diagram. So this is where you take these two molecules to go through a reaction, this energy is used to form caffeine down at the bottom right. Now, the way I explain this, especially to high school kids, is imagine that every single day when you were walking home, you'd have to walk over a pretty significant hill every single day just to get home. That would obviously require a lot of energy. However, if you could build a tunnel that goes through that hill, that would make it so much easier. And that's exactly what catalysis does. It provides a new way to reach your destination while expanding less energy. So this is one of my favorite things to teach people, is catalysis makes existing chemical reactions easier and faster, but the biggest deal is they allow the impossible chemical reactions to become possible. Things that were not known on a Tuesday can now be performed on a Wednesday. All right, now many of the chemists here will have their favorite catalytic reaction. I'm going to show you my favorite catalytic reaction. And this is the population of our world over time, over the last 2,000 years. And you can see the population is pretty baseline, it's pretty flat. And then at the beginning of the 20th century, there's this inflection, and it goes flying up to 8 billion people. We now have 8 billion people on our Earth. And as it happened, you could not have 8 billion people on our Earth if it wasn't for this one catalytic reaction. This is the conversion of nitrogen over to ammonia using a catalyst. So why do we need this to have 8 billion people? Well, it's very simple. We need that ammonia to make food or make crops. Without those crops, we couldn't feed 8 billion people. And one of my favorite sort of factoids that sort of comes out of this is that if you actually think of your body right now, and you think about all your protein, your DNA, and all your tissue, all the different nitrogen atoms in your body, 50% of those come from a factory in Germany. And if that doesn't freak you out, nothing will. All right, that's an amazing sort of factoid. The other bigger picture ones are that 90% of the world's chemical reactions use catalysis, at least on scale. And global GDP right now is estimated to be about 35% on catalysis. And if we do think about sustainability, etc., so catalysis is extraordinary. So that's the catalysis part, but what does the organo part actually mean? So I'm going to take you back to 1996, and I'll explain why in a few moments. But one of the questions you can ask yourself are, what are the branches of catalysis in 1996? And there was really two. There's two major ones. The first one was biocatalysis. There's tremendous biocatalytic work that's going on here. I've seen some of that today already. And the other major branch of catalysis is metal catalysis, homogeneous and heterogeneous metal catalysis, which was developed by humans in a lab to do catalytic different processes. Those were the two main ways. So why 1996? Well, 1996 is when I finished my PhD down in Southern California and decided I wanted to do a postdoc. So I went over to Harvard in 1996 to work for this guy. His name is Dave Evans. He's no longer with us, but he was an absolute incredible sort of pillar of the field of organic chemistry, really sort of one of the founding fathers, in my opinion. And he was also a master in the area of using metals to do catalysis. So I went to Dave's lab to try and learn about metals. I learned about all these different ones. Really, it's incredibly educational, and I really learned so much. But at the same time, every single day, I would spend a lot of time in this contraption. So for those of you who don't know what this is, I know the chemists know what it is, but for the non-chemists, this is a glove box. And a glove box is where on the inside you have a different environment from our normal outside environment. So our outside environment, we have moisture, we have air, we have oxygen. And the inside, we typically have an inert gas. And the reason we have that is because we're working with molecules or catalysts that can only really exist in the inside of this glove box. So, but practically, I've spent 2 years in my postdoc, and I spent about 8 hours a day in a glove box. And after 2 years and 8 hours a day I've been in a glove box, I started to think, why are we doing this? Why are we spending so much time in a glove box every single day? So there's a really easy way to sort of think about that, and to think about the typical metal catalyst, at least that we were working with. This is it shown here. And even if you're not a chemist, you can look at that and sort of see that you can split it right down the middle. If I split that down the middle, and you can effectively break it into two different parts. You've got the right-hand side, and you've got the left-hand side. Now, the right-hand side is the metal part. Now, some metals, but not all metals, but some metals can be expensive, they can be toxic, they can be difficult to work with, and that's why you have to use a glove box. Palladium is probably my favorite example to talk about. Really only been using palladium on it for about 150 years, but if you look at palladium resources, we only have enough palladium to last another 90 years, then we won't have any palladium anymore. If you think about that, that's scary, that's actually incredible. Now, if you look at the left-hand side of this catalyst, this is the organic molecule. Now, typically, not always, but typically, organic molecules are inexpensive, they're safe, and they're sustainable. And that's because they go back into the life cycle. All living materials are in a life cycle. We pass on, we get recycled, we come right back out as usually as other kind of inert material or some living material. So it's very sustainable to use organic molecules. So based on this, we started to think, well, what if you only use the organic part as the catalyst? And this eventually became known as organocatalysis, organic with catalysis, organocatalysis. All right, so in 1988, I got a job as an assistant professor, and this was up north from here, up at Berkeley, and this is my first group in our first year, and I love this photograph because it's 10 past 10 on a Friday night, and there's this young lab, we're in there working really hard, trying to have an impact, trying to make a difference. And what we were going to work on was organocatalysis. Now, it wasn't called that at that time. In fact, it wasn't even a field at that time. But the reason why we were excited about it was for all the reasons I've mentioned already. All of these molecules are really broadly available, or should be available, from nature's building blocks. We know organic molecules are typically not sensitive to water or to air. Because they're so abundant, they're often very inexpensive. You don't need these glove boxes, these contraptions to actually use them. And they're non-toxic. Typically, they're sustainable, they can be removed from waste streams. There's all these different aspects of them that at least looked advantageous. Now, it turns out that was not really the reason I wanted to work on this. I was sort of focused upon the idea, could you actually come up with a concept that would allow these organic catalysts to actually work, not for one reaction, but for hundreds of different reactions, and maybe this could become a field of chemistry. That was a very grandiose idea, especially because I had absolutely no idea on how to do that, like zero ideas. I knew this would be a good thing, I had zero ideas on exactly how to do it. But one day, and this was my first year, this was Tristan Lambert. He was a first-year graduate student, and he's now the chairman of the chemistry department at Cornell, so he's grown a lot since then. But he asked me about a mechanism of a really simple organic reaction. He said, what is the mechanism of reductive amination? And being a young professor, I ran to the board to sort of teach him, and I drew up this mechanism. And it's basically this carbonyl and this amine reversibly forms an aminiamine, but it's only when it's the aminiamine can it do the subsequent chemistry. And right then was where I had basically the quintessential eureka moment, because I realized that looks a lot like a field of catalysis that had basically used metals, where you could take alpha beta unsaturated aldehydes now to form aminiamines. That looks exactly like the same type of chemistry, but where you had used metals before, maybe you could use an organic molecule as an amine. All right, now for the chemists in the audience to sort of show that in a little bit more conventional format, this is LUMO-lowering catalysis. This equilibrium is LUMO-lowering catalysis. And basically, there's hundreds of reactions that perform using LUMO-lowering catalysis with metals. This bottom one would now be using an organic molecule to also do LUMO-lowering catalysis, but there basically wasn't any examples of anyone having done that before. But if it did work, it would mean that you could possibly have hundreds and hundreds of reactions that you can now do using these organic molecules. At least that was the idea. So we set out to test it, and this was the very first experiment we ever performed. It was by a student in my group called Kateria Wren. She's a young first-year graduate student. This is a transformation called a Diels-Alder. These are the two different molecules we're going to try and combine with each other to form this one over here. But the big difference over the reaction arrow, there's not a metal, there's actually an organic molecule that we will hope will be the catalyst. So when we performed this, what you see, if it goes all the way at the bottom, it worked. It actually worked, which was incredibly exciting to us. And I always remember at the time the student told me the result, she told me it worked. I thanked her very nicely. I didn't, for reasons I'll explain later, I didn't want to look too excited, but I thanked her and I left the lab. I went into my office, I closed the door, I locked the door, I closed the blinds, and I jumped up and down for about 10 minutes. I actually called my wife at the time and said, you won't believe this, but I think I just got tenure. And now, for those of you, you obviously understand, you know, when you're a young assistant professor, you're keenly focused on tenure. And at this moment, it felt like we were in an opportunity of doing this. Okay, so we had to publish the paper. So the first thing is we had to give it a name. We came up with this thing called organocatalysis. We gave it this name, organocatalysis. And you might think, well, naming things, is that important? And as it happens, naming things is incredibly important. So for example, this is Jean-Jacob Berzelius. He was a scientist in Sweden in the 1800s, And he came up with all these words that we now use in modern chemistry and modern science. Things like catalysis, protein, polymer, isomer, organic, inorganic. He came up with all of those words. And naming things is important because it gives you a framework from which lots of other people in the community can understand what we're all talking about. It's the umbrella from which we can develop fields, basically. So in the modern sense, directed evolution, AI, machine learning, nanotechnology, organocatalysis, these are words that allow you to understand what area of science we're actually talking about. But the second part of this was we introduced the concept of a generic activation mode. That's a very fancy way of saying what we stated was this idea shouldn't work for just one chemical reaction. It should work for hundreds of other chemical reactions. So that was a very bold thing you put in your first paper because we actually had only performed one reaction, hadn't performed any other ones. So now we had to go off and do that. That was our first catalyst that we'd actually developed. So this was the first reaction, the Diels-Alder, and we went off to test it in other transformations. What we found, it went bang, bang, then it stopped. It stopped working after 3 reactions. So this was really awkward. This was really embarrassing because I've told the world this is going to work for hundreds of reactions. There's only 3 of them. So very fortunately, though, I had 2 really amazing young graduate students by the name of Joel Austin and Chris Borch. And they came along and said, we think we can do precision molecular engineering to take a catalyst that only works for 3 and convert it into a reaction that works for many, many different transformations. And it was basically the idea to remove a carbon from down here and put a T-butyl group up there. Now, when I explain this to non-chemists and try and make sense of it, I say this precision molecular engineering, looking for a great outcome, is a bit like precision athleticism, looking for a beautiful outcome. And this is Zlatan Ibrahimovic. If you haven't heard of him, he's a world-famous soccer player, and he plays for Sweden. He's viewed as a sort of football god. And he has amazing outcomes when he plays. And I'm just going to show you one of them. All the way back there, let's go to this amazing goal. Fantastic. Now, I actually put this video in my Nobel Prize address. And the day afterwards, all the newspapers in London got really upset with me. And they all said, MacMillan showed this video only for one reason, and that was because the goal was scored against England. Which is and I think that was a little bit unfair and a little bit insulting, but let's watch it one more time. Look at this, look at that. Wow, look at that. That's incredible. That's just utterly fantastic. Okay. All right, so the key question here is, basically, that original catalyst worked for 3, where we're going to have this precision molecular engineering to have a good outcome, and sure enough, when we went to the 2nd generation catalyst, it now went from 10 to 20 to 40 to 50. Other people started developing their own versions, and it went into the hundreds of different reactions you can now use with organocatalysis, which was great. Now, the other question people always ask is, what are the applications of organocatalysis? And there's a lot of different ones. I'm just going to show you 2 because I think they're pretty cool. The first one is it's now used worldwide to basically make flavors and fragrances. If you think about perfumes are actually made on a pretty enormous scale and consumed on an enormous scale worldwide. And one of the ones which was developed was by Firmenich, and they can actually now make Lily of the Valley, and it used to take them 6 chemical steps to do it. And they can now do it in 1 chemical step using organocatalysis, which was something which was really cool to see that you can now do it in 1 chemical step. But without question, the #1 application has been for medicines. This is just one of them. This is a Merck development called talsegipam to treat migraines. Migraines basically impact about 3% of the population. And so there's a big need for migraine treatments. The reason why I like to show this one is because it uses exactly our chemistry to make this type of molecule. But even more recently, I was just actually at Merck last week, and they were showing me actually a cancer treatment they're scaling up that has 2 organocatalytic reactions and a transformation also in biocatalysis from Francis Arnold, who I think is also coming as part of the seminar series as well. So it was really cool to see these different technologies all being employed to make this one cancer treatment. So one of the parts you have to think about is, basically this idea of this growing population of our Earth, and how do we continue to develop catalysis in a responsible way. And what's been fantastic about being here this morning is this is a slide that I didn't just put this in because of what I learned this morning. This is a slide I show all over the world is when you think about catalysis for the future, I think these are some of the technologies we have to think about. And what was really cool was seeing how much these are being employed here. Biocatalysis, photocatalysis, electrocatalysis, organocatalysis really is cool, but we will have to invent other forms of catalysis as well to sort of keep up with that. Okay, so I'm going to finish off in the next, I think, how much time do I have left? I'll be done in 20. I'll be done in 20. All right. So I wanted to sort of finish off by telling you about other ways you can think about sustainable catalysis, but now with photons, and I'm going to get a little bit more technical now. And so this is not organocatalysis, but this is something we started to work on after organocatalysis. And we started to think about there's all this fantastic science that's been performed by inorganic chemists who are trying to figure out ways to power the planet using solar energy. And we started to think, could we take all the knowledge that they had learned and export it into organic chemistry to try and develop some new organic transformations. And ultimately, this has become known as photoredox catalysis. This is the idea of organic chemical reactions being powered by visible light, things like blue light, which is actually being shown here. All right, now, photoredox catalysis has really taken off enormously in the last, I'd say, 20 years or so. And I can sort of show you this. This is publication numbers alone. And this is just to sort of describe or give you some kind of context behind what I'm about to show you. But it really has become, it's even bigger than organocatalysis. It really is. I think you can't open up a journal now without reading about a photoredox or a photocatalytic process. So I think it's fair to say that the impact of it is certainly there. So the next question is, why is that? Why has it become so heavily deployed over the last 20 years or so? Well, it's really simple. It's because most organic molecules, not all, but most of them are colorless, meaning they do not absorb visible light. However, there are these photocatalysts that are out there that are absolutely fantastic. They've been able to specifically pick up photons from visible light. For example, blue light, green light, in some cases red light. In this case, this is an iridium photocatalyst. It's got an energy of about 60 kcals per mole of energy. Okay, so you might wonder, well, why is that interesting? Well, imagine I have a reaction vessel such as the one which is shown here, and you can see, hopefully you can see this, but there's a whole range of organic molecules there, and there's a photocatalyst right in the middle. Now, if we zoom in on that, so it turns out these photocatalysts are incredible. It's selectively been able to pick up those blue light photons, while all of the other molecules will not. So it's very selective at being able to take that photonic energy. But this is the really important part. When it picks up that blue photon, it goes into the excited state, and when it's in the excited state, it's basically at the equivalent of 32,000 degrees Celsius, while everything else is at room temperature. So that's really weird, right? You've got one molecule that's basically a completely different energetic plane from absolutely everything else. So what's it going to do? It has to offload that energy. And the ways that it can offload that energy is it can give and take electrons with the organic molecules that are around it. Now that sounds kind of chaotic, but it's not chaotic. It turns out these catalysts are incredibly selective in how it will give and take electrons to these molecules. Now, the second thing I'll show you before I demonstrate this is that all of these organic molecules are really low energy molecules. They're molecules that we think of as being really stable. But yet, when you shine light on this catalyst, and then this catalyst gives and takes an electron, it basically, as it does that, is taking these really low energy, broadly available molecules, ones we think of as being really stable, and turning them into these really high energy species along the way. So it's basically taking carboxylates, making them into electrons through decarboxylation, halides. You can even take CH bonds, such as one shown here. Again, making really high energy species from these really stable molecules. Okay, so now that you can form all of those radicals, what are you going to do with it? Well, this has been the other part, is over the last 20 years, there's been just an enormous number of transformations that have been developed, We introduced the first one, which was an alkylation reaction. Teschik's Jung group introduced this beautiful reaction for doing 2+2 chemistry in terms of cycle additions, but the list goes on and on and on. So there's literally hundreds and hundreds and hundreds of new chemical reactions that you can perform simply by setting up a blue light shining into a vessel that has this little catalyst associated with it. Okay, now it really has become heavily adopted by the pharmaceutical industry. Every pharma company uses it, and I'll explain why. The reason is simply because it effectively allows you to use completely different molecules to build drug molecules. And the way that pharma was working was it would basically take aromatic rings and plug them together to make drug molecules. And the reason it would do that is because they had great technologies to basically connect aromatic molecules to make these ones which are shown here. But pharma has started to realize that these molecules becoming drugs is more of the exception than the rule, because they have a lot of properties which are actually not very good in terms of solubility and how they interact with the human body. So the reason why they became really excited about photoredox is you no longer have to use those aromatic compounds. You can use all of these aliphatic systems. And that's exactly what they're hoping to do, is to put all these sp3 carbon-rich molecules into drugs. So using this and using the same Lego analogy, you've now got completely different systems. You've massively blown out the types of shapes that you can actually access. And as a result of that, you can build far more complex Lego-type structures, but in this case, far more aliphatic-type drugs. And these have a much higher success rate in the clinic. There's been this big Moneyball analysis on this for what molecules are successful in the clinic. It turns out are the ones which have all these sp3-rich carbons. All right. So with this in mind, lots of different pharma companies are now using this. Basically, every pharma company is using it. I thought I'd just very briefly just show you a couple of different examples. It's been used heavily for drug discovery in a high throughput fashion. Most pharma companies do photoredox on high throughput using robotics and robotic setups. Here are just some examples. This was a Lilly molecule, it's a JAK2 inhibitor that was made using photoredox. This was DNA-encoded libraries, which a lot of people now use. This was developed in Novartis, and basically Gilead have developed these antiviral nucleoside analogs using photoredox, and Merck have introduced these peptidome mimetics. Again, these are just a small selection of some of the drug molecules that have now been made using this photonic approach. But those are obviously on small scale. You now have to be able to scale it up. Photo is getting up there in terms of scale up. It's up to about a ton scale now. This is one approach that was developed in Merck process chemistry. A ton is obviously still not quite there. This is a sort of a message that you probably hear over and over again. In China, they're actually accelerating that much faster than is happening here. And they've now got multi-ton photoredox reactions going forward in China, sort of as we speak. But I wanted to finish off just to sort of show you one other aspect about this, which is the idea of being able to use this technology. And everything I've shown you up to this point has been using photocatalysis. But one of the things that we became really interested in a few years ago was the idea of could you actually combine photoredox catalysis with traditional metal catalysis. And the idea here was by combining them, could you actually come up with some really interesting new transformations? So the really simple idea we had was, for example, if we were to take an aromatic bromide with a nickel system, all the chemists here will tell you, well, we know that the organometallics of that is that nickel will do an oxidative addition and to give you a nickel aryl species, nickel 2 species. Now, Greg Fu and others have beautifully demonstrated that if you generate a radical in the presence of a nickel 2 aryl species, this radical will undergo an addition to nickel and then do reductive elimination to form a new bond. Now, I've shown you, hopefully, that one of the things photoredox is amazing at is being able to generate radicals from all these new, abundant, readily available start materials. So this means you should start to be able to do cross-coupling from all these abundant organic molecules, at least in principle. So the one we thought would be interesting, what if we took amino acids, abundant biomass such as amino acids, such as proline, could you effectively shine light on it? And in doing so, would it perform a one-electron chemistry? It would decarboxylate to generate this radical here, and then that would undergo an addition and then reductive elimination to generate that type of product. That was the idea behind it. Could you effectively use amino acids to do cross-coupling? So this was the very first paper we ever published on this. This was in Science in 2014. And I think it's fair to say that we took this concept and we picked it up and we ran with it. And we published lots and lots of, we published about 50 papers in this area. But lots of other people have also published in this area. Phil Barron has some really beautiful work of doing this now with electrochemistry. Dan Weiss has shown you can use reducing metals to do effectively the same thing. So this nickel-type catalysis has really exploded in a big, big way. Okay, so one of the ways, though, we started to think, is there other ways of being able to join molecules together, to do cross-coupling? And we started to think about this mechanism known as SH2. Now, for chemists, SH2 is not a mechanism that people think about heavily. I didn't even know what SH2 was 6 years ago, to be completely honest. But a reason, or why we ended up working on it, was because we started to realize the world is really focused upon trying to get more and more sp3 carbons into drugs, into flavors and fragrances, into lots of different types of molecules. And again, this idea, can we harness abundant materials, was really important to do it. All right, so I'm sitting in my office one day thinking, how can we start to come up with new reactions that will cross-couple sp3 carbons with sp3 carbons? And I thought, well, photoredox is great at generating radicals. Would it be great if we could just generate two radicals around about the same time, and we know that for them to connect with each other, it's effectively barrierless. Could you get a cross product? And immediately, all the chemists in the room are going to go, there's a huge flaw in this way of thinking, because if you generate two radicals, because it is a barrierless process to react with themselves, they'll react with themselves to homodimerize from the tertiary to the primary, and you're just going to get this unholy mixture of lots and lots of different products. But unperturbed by this, I convinced a postdoc to go off and try this. The postdoc came back and said, yes, it was a terrible idea. We created all these different byproducts. It was a disaster. But being a good postdoc, he said, but I've had a different idea with a similar type of concept. It's like, what if we just borrow the way nature does this kind of bond formation? Because what nature does, it does this thing called SH2, and it does it with cobalamin. And this is the idea that cobalamin will take a methyl radical, and that methyl radical will sit on cobalt, and a radical will come along and do SH2. And if you're wondering what SH2 is just a radical version of an SN2 reaction. You think back to sophomore organic, you learned SN2, SH2 is just the radical version, but you have a radical leaving group. Now it turns out metals leaving in a different oxidation state are a fantastic radical leaving group. There's been all these great statements about how basically SH2 is completely underutilized in chemistry, and so we started to think this could be a really fantastic design principle for new ways to join molecules together. All right, so with this in mind, we decided we could employ this. Now you're probably wondering, how would this work? Why would this take two radicals and make them selectively react with each other? And here was the basic hypothesis, a very simple idea, and it was that if you got a primary and a tertiary radical, we believe the primary radical should add to the catalyst, and then the tertiary radical is really nucleophilic, and so it should do SH2 to give you the cross-selective product. But you're probably thinking, okay, that's fine, but why doesn't simply the primary radical react with itself? Well, as it happens, primary radicals are really not nucleophilic, so we thought there's no way this is likely to happen. And then the second part is, well, why wouldn't the tertiary radical first of all add to the metal, and then it react with itself? And the problem here is that a tertiary radical adding to that metal is basically an incredibly weak bond. We think it actually would never form for many different metals. But even if it did, it's so sterically encumbered that this thing is never going to add to it to form that product. And so there's only one pathway available to it, the original one of doing this cross-selective. Now this is something later on we call radical sorting, because the idea the radicals will sort themselves out through this mechanism. But at the time we wanted to test it, we published this paper back in 2021. We did it as a collaboration with Johnson & Johnson. But the idea here was, could we take basically an ester group with a redox active ester on it, fully substituted carbon, and have it form a tertiary radical, have an alkyl bromide form a primary radical, and have them cross-selectively couple with each other through this SH2 mechanism. So just to sort of show you, these are basically all the different alkyl groups and the different acids at the bottom. When we performed this reaction, what we found was it was highly cross-selective. to react with each other with really good levels of efficiency, which was obviously something we were very excited about. All right, now we published this, as I mentioned, back in 2021, and again, we've sort of taken this to the map, we've taken this to the bank. The first question we had is this radical sorting mechanism genuine? It seems too good to be true, right? I can generate a primary radical and a secondary radical, or a primary radical and a tertiary radical, and they will selectively find each other and react with each other just by forming them. And the second one was, well, we showed it worked with iron. Does it work with any other metals? Now, in the literature, there's only 4 metals which have been shown to do SH2 chemistry. But we've now performed enough experiments, we've now found 11 different metals that actually do SH2 reaction. And that's crazy, that's just not known. But the nice thing about it is it gives you lots of new levers from which you can actually start to do lots of new chemistry. All right, so I'll just sort of show you basically how we've taken this to the bank. We've published, I think we've now have 15 different papers with lots of different catalysts that we do this. These are just some of the papers that we've published with SH2. What's been even better is to see other people gravitate into this area, because this is a useful mechanism. Ryan Shenvey, Phil Barron, Matsunuga, Ko, Yang, they've all started to do SH2 chemistry as well now, which has been fantastic to see. We want this to go as far as wide as humanly possible. But I'm going to finish off with one transformation, and it's one that I think is pretty cool, and sort of demonstrate to you how there's really nice ways to think about the utility of this reaction, this mechanism. So one of the things you realize is you can now start to dissect any molecule in completely different ways, as long as you can get to a primary radical with a secondary, or a primary radical with a tertiary radical. So for example, here's a reasonably complex molecule, and if I looked at that bond there, and I sort of broke it apart there, I can imagine I could literally make that bond just as long as I can form the 2 radicals at those 2 positions. Now, I've already told you that photoredox is amazing at making radicals from almost any functional group now. So the nice thing is, it doesn't really even matter what my start materials are. As long as I can form radicals from them, this chemistry should work. It's basically functional group agnostic. It doesn't care just as long as you can make a radical. So based on that, we said, well, if you can use any functional group, which one would you want to use? And the one that we came up with was, could we use alcohols? Could we literally use alcohols? Now, I'm making it look like we came up with this in the last 2 years or so. This is actually a reaction my group's been working on for 17 years, unsuccessfully, until we eventually got this one to work. So you might be wondering, why on earth would you ever want to work on something for 17 years? And I'll try and make the case really quickly. So for example, if I go to Aldridge or any basically chemical catalog, and I look at the abundance of all these different functional groups, alcohols, acids, chlorides, halides, boronic acids, etc. This is the relative abundance. There's so many alcohols. Alcohols blow away everything else in terms of abundance, almost everything else. And so if you think about, if I was to take, for example, these two molecules that are 2 different bromides, and I wanted to cross-couple those, if you think about the molecular space I could generate, that would be it there. If I thought about an organometallic, all of these different halides, which is shown there, that would be the molecular space. But if I just look at the alcohols, and I think about if I'm going to take 2 different alcohols and cross-couple them, the molecular space you can build is enormous. So to us, that made a huge amount of sense. That's exactly what we should be doing. So here was the idea. We would take 2 different alcohols, we put them in the same vessel, and we invented this new reagent that everyone now uses, especially across pharma. It's called NHC, it's commercially available. And you throw this NHC in, and it reacts with both those alcohols. And after it reacts with them, it forms this adduct. And under photoredox conditions, it then forms a radical at this position on both of them. It undergoes beta scission of the carbon-oxygen bond to generate these aliphatic radicals. And you've now generated 2 radicals in the presence of your catalyst. Now remember, only the primary one is going to add, and then the secondary one is going to be the one that's going to do the SH2, so it should be really cross-selective. So you're just taking 2 alcohols and crossing them onto each other where those 2 alcohols were in the first place. So this was, again, a really fantastic collaboration with J&J. This was a paper that we actually published last year. It's very rapid sort of uptake, and I'm just going to show you basically a couple of examples. So these are some of my favorite ones. For example, here are all secondary alcohols. And we simply take these secondary alcohols and we add methanol. And we're going to ask methanol to deoxygenate, and this to deoxygenate, and put a methyl from the methanol. And so if you do that, that works really beautifully. It cross couples to form those products simply with methanol and those alcohols. You can actually even take primary alcohols with methanol, and it will actually do exactly the same chemistry, because we found methanol even has different chemistry from other primary radicals. It's even more reactive, which is useful. So there's some really cute things you can do with this. For example, I can take a peptide, which is based on threonine, and can actually convert it over to a peptide which is based on valine simply by adding methanol to it. And if you actually do this, this actually works really nicely to be able to do that conversion. So this other one I thought was pretty cool, this idea that we can now also take effectively any tertiary alcohol and effectively make quaternary carbons from it. Quaternary carbons are really hard to make in organic chemistry. So, but at the same time, tertiary alcohols are really easy to make. So the idea here was, could we take any ketone? Can we then take, for example, from Aldrich, any organolithium or any Grignard, make a tertiary alcohol, such as the ones which are shown here, and then simply add in methanol, and as a result of adding in methanol, now you can form these quaternary carbon centers. That's exactly what we'll be able to do. All right, the one other aspect of this, which I'll just show you really briefly, questions that everyone asks me wherever I go is, how do we know which alcohols will selectively react with other alcohols? And it's really simple. You can break them into these 4 groups. And these 4 groups, we know that methanol, for example, will react with other primary alcohols. Methanol will also react with secondary alcohols. Methanol will selectively react with tertiary. But you can also take these primary alcohols with secondary and also these primary alcohols with tertiary and make those as well. Very selective in reacting with each other. All right, just to sort of finally drive this all home, we were able to take, for example, this alcohol, which has a primary and a tertiary. This is a secondary alcohol. We can actually get those 2 things now to selectively react with each other through this approach. If we now take that chemistry, put it together, the idea is connecting those 2. When we perform this chemistry, it actually works at 51% yield. But what's really nice is we can then take the resulting alcohol, which is left over, and perform one more transformation. All right, that's normally where I finish my talk. I have 2 more slides, and I have to just point this out. Now, one of the reasons why I was so excited to sort of come here today was I just told you that this SH2 chemistry uses alcohols, and alcohol is one of the most abundant things in the world to actually use to do cross-coupling. It turns out there's one functional group which is actually more abundant than alcohols, and that's CH bonds. And so the idea was, wouldn't it be great if we could selectively do CH abstraction and get molecules to dimerize with each other? And talking to various aeronautical engineers, actually, people started to ask me, well, could you take things like the really heavily abundant lower alkanes like hexane or pentane or heptane or octane, and could you start to dimerize them? Just simply using light, either blue light or sunlight or whatever, to make these things. And the reason I put this in, because I know that everyone here is very familiar with things like jet fuel, JP5, but a lot of these higher alkanes obviously have very good flash points and other things like that. That could be pretty interesting. And we now have proof of concept on this. We can actually now dimerize these molecules. But one of the key things is dimerizing them without polymerizing them. And we now believe we know how to do that as well. I'll save you all the reasons why we think this would be interesting, but we do think that this mechanism could be really valuable to people who are thinking about taking lower alkanes and making them into anything which is going to have higher energy density associated with it. All right, I've probably went way too long. I will finish off there. I will thank, this is my lab. We have a pretty big group. It's about 45 people. This is us over at Princeton. It's an amazing group to work on. We work on everything from SH2 with CH bonds to physical inorganic spectroscopy, all the way over to chemical biology. As Steve mentioned, we're working with Ludwig on new cancer approaches as well. But all of it is fundamentally based upon understanding new types of chemical reactivity and catalysis. I'll also finish off by thanking these people who funded us, and not least of which is ONR. It's actually been very a great collaborator for us on a whole range of different projects over the years, but also has the pharmaceutical industries as well. And then finally, I know I'm getting hot up here, as you can probably see. I know it's been it's not always easy to sit in hot weather and listen to someone bang on about chemistry, but I'm really grateful for your attention this afternoon. If there's any questions about any of this, please ask me. And honestly, if you want a photograph of the medal, come and take a photograph as well. Thank you so much. critical that we're trying to get away from metals, and then all of a sudden we're back into using metals. But one of the things which I've sort of realized along the way is, so the organocatalysis component was really focused upon how do you scale up chemical reactions in a way that makes sense and are actually suitable for everyone. And as I said earlier on, there's certainly metals which are not problematic, like iron, other abundant metals, but there's a lot of metals, including iridium, which are problematic, that are rare. But what we're doing in the second part, we think, this is the way at least I rationalize it, is that we're trying to come up with completely new chemistry concepts or mechanisms that people will be able to sort of understand the value in and make useful molecules in discovery, which is exactly what pharma do. Pharma are making molecules, discovering molecules, but then when it comes to scale up, then you know the molecule you want and you can scale it up to do exactly that. The second thing that's happening is there's become this huge cottage industry now, and how do you build sustainable photocatalysts? So we're using iridium. Iridium's great because it gives you quick reactivity understanding. It gets to chemical reactions you care about. But once you've got the reaction, then you can go back and reverse engineer it to come up with a new photocatalyst that will be scalable and is no longer a problem from the metal point of view. So I think all the principles still hold completely. You still, I mean, the reason people are still using organocatalysis is because it is cheaper, abundant, more sustainable. And if there were cases where people could get away from palladium, they would. But at the same time, I think you don't want to throw away the conceptual component of it, that you can absolutely invent new mechanisms with some of these metals on a small scale and then go back and reverse engineer it to come up with much more sustainable catalysts for a larger scale. At least that's the way we're thinking about it.
Is there any current effort ongoing to seek out an organic separate operated aerial and perform the function of the metal that you're using now?
Yeah, that's a great question. The question was, is there anyone developing photocatalysts that are organic instead of metal-based? And the answer is yes. So there's a whole bunch of people who are doing that. The tricky thing is, they're fantastic for scale-up, but they don't have so once you've figured out the reaction you want to scale up, then you can employ it. The problem is at the beginning part where you're trying, just say you're trying to run, say Merck is running 4,000 chemical reactions. If they try and use 4,000 organic catalysts to do it, it doesn't work because the scope of it is just poor. But you can use iridium on a tiny scale for those and find the reaction you want and then plug in the organic catalyst you need when you need to scale it up. So your instincts are really good, and there actually are people developing it. The other really interesting thing, and again, to show that I'm hopefully not beating up on metals too much, there's also the development of first row transition metals, which originally, based upon the physics of it, at least the physical and organic component of it, people thought it would be impossible to use first row transition metals to do photocatalysis. It's now been found there's a loophole, and the loophole is the inverted Marcus region, which now allows you for certain metals like cobalt to do photocatalysis when people originally thought you couldn't. So it's really a beautiful sort of ongoing development in different types of catalysts that are being developed.
Has any of the work that you're doing led to understanding of reactions that occur in nature? Were there already?
Yeah, that's a great question. So what was kind of funny and ironic was the first reaction we did for organocatalysis was this Diels-Alder reaction. And we did it because we thought that would be really cool to do an organic molecule, because there's no enzyme that does Diels-Alder reactions at that time. And then subsequently people found there were. So we actually did the small one, which was subsequently discovered thereafter that nature actually did something that we were already doing, which was pretty cool. Now, Diels-Alder had happened in nature, but they didn't know that there was an actual biocatalytic way to do it, and that was discovered after we had actually done it. So I thought that was a kind of neat outgrowth of doing that. What's been really, even for me, even cooler, and maybe Frances will talk about that when she comes here, is people can now take our organocatalytic reactions we're developing where there isn't an enzymatic version, and they can now effectively build in to enzymes those functional groups to do these organocatalytic reactions now on an enzyme that nature didn't do before. It's called new to nature. which I think is a very clever way of framing it. But now you can build in the functional groups to do exactly that.
Thank you so much for being here. We would really like to recognize this, and we put together a little award here. You kicked us off with an amazing presentation. You're the first one to do this for us. And we've got a small award here, and I'll just read the citation on it. It says, Sir David MacMillan, PhD, with gratitude for your contribution as a distinguished lecturer. Thank you for your commitment to advancing innovation and the Navy Tech Connect mission to connect ideas, technologies, and people in support of warfighting. Thank you so much.